Hi all, this is Mr. Yeager for Honors Chemistry. We are checking out the topic on periodicity today, which basically means we're trying to break down the periodic table and understand the trends that develop on the periodic table, and again, the chemical reason behind those trends. So, here we go. Okay. So, first off, let's just talk about where did the periodic table kind of come from. It started with a man named Dmitri Mendeleev, who really kind of consolidated a number of different scientists that kind of were trying to create different organizations for the elements, but Mendeleev did it. That's why he's called the father of the periodic table. He organized the elements in rows based on atomic mass, though, okay, where he did see quite a few trends, okay. He also tried to then set up the columns based on similar properties. Now, one of the interesting things with Mendeleev is he really actually didn't do any serious experiments from a chemistry standpoint, but he organized the data. That was kind of his big contribution. Is he was very much a data analyzer and was able to see the trends and of the properties and the atomic mass that developed and created a table out of it. The thing is, it did leave a lot of empty spaces. He purposely left spots blank in the table, where basically if we look at the modern one, there would be a box that just nothing would be in it, all right? And he would hypothesize that these would probably be new elements that we just haven't found yet. Now, one of the amusing things was when these would generally be found by somebody, he would then try to take credit for it because he was like, I knew it was there, but he never actually would discover any of them himself, okay? So that's what, I mean, he is known as somebody that did actually pillage off of other people's data. One other thing that basically went on with it is that he would shift elements to make them fit even if it broke his own rules. Okay, he would kind of go around and say, you know what, this doesn't work as well, and he's going to shift the element from one spot to another. Okay. The modern periodic table, for the modern periodic table, that was Henry Moseley that helped develop that. He organized based on atomic number. Okay, and obviously that's our current periodic table. All right, through the use of organizing based on the atomic number, he developed what's called the periodic law, which is again why we call it the periodic table. When elements are arranged based on their atomic number, the chemical and physical properties will repeat themselves as you enter a new row. They go row to row and do that. All right, and again, that's one of those things we're going to be investigating quite a bit. This is the trends that we would see, is that we would see this general property occur as we go across, and then it would repeat itself as we head down rows. Okay? There you go. That's why it's called periodic. All right? So here's our periodic table of elements. Okay? What we're doing here is now we're breaking up what the different groups are. What do we call them? So there are 18 columns across the periodic table. We kind of ignore the bottom two rows. And each column is called a group or a family. And again, that's because elements in the same group, in the same column, have similar physical and chemical properties. It's also known as family. The more common term is definitely group. Okay? There are 7 rows on the periodic table. 7 rows. I'll write those out. 1, 2, 3, 4, 5, 6, 7. Again, we saw that when doing electron configuration. These rows are called periods, all right? Again, because we're going to repeat the same set of properties every single period, all right? So we could possibly identify an element. If I said, what element is in group 1, period 2? We can go to the first column, the second row, and that would be lithium. Please, please, please recognize that the first row here, row number 1, is hydrogen and helium. Like, that is one row, and those are the only 2 elements in it. Okay? So row 1 would only have group 1, row 1, and group 18, row 1. So just be aware of that some. Okay? The second one on here, germanium, GE, is in group 14. So I come all the way over to group 14 and then go down 4. Remember, there's no, like, we have to count the empty space up here. So 1, 2, 3, 4. They're in period number 4. Okay? So groups are columns, periods are rows. All right? The classifications of the elements, basically metals, nonmetals, and metalloids. Okay? I'm going to first point out the staircase because that is really what tells us where the other 2 classes are, the metals and nonmetals. So we have this staircase area, all right, starting with boron and then basically going diagonally down. You are not going to be responsible for specifically knowing every element on the staircase. We should know at least the diagonal, and then you have germanium and antimony, Sb, that follow along with it, okay? But know the diagonal, all right? These elements are called metalloids, or semimetals, all right? So we have the metalloids right in the middle, and there's a reason we call them that, semimetals, part metal, because they are kind of a combination of both the metallic and non-metallic properties, okay? The nonmetals on the right, okay? They are, that's all I need to say, nonmetals on the right of the staircase, but don't forget hydrogen over here. Hydrogen is also a nonmetal. It just has to be placed on this side because it reacts more like group 1 elements, all right? So that's kind of your little exception where you do have one nonmetal on the other side. The rest of the whole periodic table are metals, okay? Everything else on the periodic table is a metallic element. So metals on the left, nonmetals on the right, metalloids on the staircase, okay? To kind of hammer out different properties, you can see the big list there, okay? Metals are generally solids. They come in many colors. They're malleable and ductile. Malleable means they can be made into foils. Ductile means they can be made into wires. They're good conductors of heat and electricity. That means they heat up quickly and they also cool off quickly, and they also allow the electrons, electricity to run through it. They have low specific heat. They form cations, as we already learned. They have what's called a low electronegativity. We'll see what that means in a moment. And then they react with acids. I know it seems kind of random, but that's actually one of the properties of metals is they react with an acid very well. Okay, they want that hydrogen atom reacts with it. Okay, metalloids, there's not a lot to say about them. Like it says, they have varying properties, very similar to metals and nonmetals. The only thing that I can really point out with metalloids is they're good semiconductors, which basically we use in computer chips. Okay, so these are things that they conduct a ton of electricities at lower temperatures, and then their conduction kind of decreases as they get warmer and warmer. Okay? Nonmetals are usually gases. They have low melting points. They're generally dull and brittle, essentially all the opposite of the metallic properties. They're not good conductors of heat. They have a high specific heat. They form anions, and they have a high electronegativity. Okay? So again, quite a few properties to kind of remember. If you kind of remember one side versus the other, you can kind of figure it out basically by thinking the opposite. And then you just have semiconductor metalloids in the middle. Now real quick, what the heck is that electronegativity? It's one of the trends we're going to be doing later, but to explain it, electronegativity is the ability for an atom to attract electrons from another atom. Basically to pull electrons from another element, all right? So metals don't do that very well, which is why they become positive. They will lose those electrons. Nonmetals that form negative ions, they like to pull those electrons away, and that's why they're negative. Okay? All right. Time to basically get the group names. Okay? What are the different groups called? Group 1, column 1. They are known as the alkali metals. The biggest thing to remember about the alkali metals, this doesn't include hydrogen first off. Hydrogen is not included. So this is lithium, sodium, potassium, rubidium, cesium, and francium. We know they form a positive 1 charge. They are very, very reactive. And the reason they're so reactive is they're 1 electron away from being stable, from getting the full octet, that they just want to chuck that 1 electron really fast away. Okay? Group 2, column 2, the alkaline earth metals, still pretty reactive. A lot of them, I mean, once they kind of catch fire, they go. All right, they can be explosive, but they're not as reactive as alkali metals. Then you have the D block. Again, we learned the D block in electron configuration. This whole section here, that they are the transition metals. Okay, they generally have lots of different properties because they can have multiple charges. They come in many colors. I mean, there's all sorts of things that transition metals can really do. It is definitely varied. Some are not very reactive at all. Some can be a little bit more reactive. It kind of just depends on which ones they are. Okay, and then the last one down here, the F block. The F block are lanthanides and actinides down at the bottom here. Okay, this is called the inner transition metals. That's because technically they're inside the transition metal block, but we kind of hold them out separately. Again, the nice thing is you can see the color coded down here to break down all the different types of elements that are on here. Okay, There's not a lot to say about lanthanide and actinide, so we do not use them because they are generally radioactive elements. All right, so I'll kind of just leave it at that. Obviously, they do form positive ions. We would just say they have general metallic properties. Okay. If we go to the other side, okay, group 17. I am starting pretty close. I'm not just going down the line. Group 17. They're known as the halogens. They are the most reactive nonmetals. So you're going to see when we do a lot of compounds have fluorine, chlorine, bromine, and iodine in it. Astatine is very rare, so we don't usually use that one too much. But those are the halogens, very, very reactive. Same reason the alkali are so reactive. Their halogens are one away from being an octet. They want to grab that electron fast. Group 18 are the noble gases. They're very unreactive. This includes helium at the top. And they're unreactive because they have the full outer energy level. As for the other groups that I did not mention, group 13 is just simply called the B group, 14 the C group, 15 the N group, and 16 the O group. So you can see that we kind of, I guess, just stopped caring about naming them. And the group 13, 14, 15, and 16 are just named after the first element in the column. Okay? There is actually, now that we know what noble gases are, where they are in the periodic table, there is an easier way to write electron configurations. And I say easier in an abbreviated way, okay? And it's called the noble gas electron configuration, all right? What you do is you simply identify the noble gas of the chemical symbol on the row above the element you are completing, okay? And I'll show this in a minute of how this works. So again, you're given an element. You go to the row above that element and go to the noble gases and write that noble gas down in brackets. This is supposed to represent all of those electrons up to that noble gas, all the inner energy levels. So in the end, all you're writing is the rest of the electron configuration, basically the valence electrons and maybe the D and F block electrons that are included as well. So you only really are writing one row of the electron configuration, the last row. So for example, with magnesium, okay, the answer is neon 3s2. I'll actually go back so you can see this some. Okay, so if I'm trying to do magnesium's noble gas configuration, I go back to the previous row to the noble gas. So I would write neon. This is supposed to represent 1s2, 2s2, 2p6, which is what I would normally do to get magnesium's electron configuration. Then all that's left is the 3s2. All right, and that's all I would write. So above here you have the noble gas configuration. Below you have the regular electron configuration. And you can see it's just something that works a lot faster. Okay, it's a lot quicker. All right. For the other one that it chose, I'm going to look at a different periodic table. You got manganese. Manganese is in the first row of the D block, so I go to the row above it, and that would be argon. And then I would do 4s2, and then I believe 3d5. Yep, 3d5. And that's your answer. That would be the manganese electron configuration. If I do promethium, I'm just going to let this one show. Xenon would be the element above the row, and this one would be a little bit more difficult because it's the row. Obviously, we've gone down into the lanthanides. Well, the lanthanides don't start till 6s, after 6s2. So above that is xenon, and then I write 6s2, 4f3. Okay, you can double check on the periodic table as needed so you can see how that works. All right. I just want to share the states of matter on the periodic table. Like we said, generally metals are solids, nonmetals are gases. All right. You can see based on this periodic table where whites are solids, and whites are almost all of the metallic elements. Okay. There are a couple of nonmetals that are metallic. Okay. It turns out, not metallic, sorry, solid. Okay. There are a couple of nonmetals that are solid. Carbon in pure form is a solid, so it's phosphorus and sulfur and iodine, tellurium, okay, and some of these down there. Okay, actually not tellurium. I'm going to skip that one. That's a metalloid. So there are a few nonmetals that are solids. Okay, we do have two liquids on the periodic table. Bromine and mercury happen to be two elements that, when pure, are in liquid form. You can see we have gases are all nonmetals. Okay, all nonmetals over here, and hydrogen. And then, I mean, we're not going to get into this too much. The yellow ones are all artificially made elements. These are all ones that are not natural, that man has actually made, humans have actually made in the laboratory. Okay? Again, mainly just showing you that so you can see the states of matter on the periodic table. All right, getting to the trends, the big last part here, okay? We're going to be looking at 4 trends on the periodic table, and basically all 4 trends can be based on what's called Coulombic attraction, okay? What the heck is Coulombic attraction? This is the attraction or force, so a force that's created between oppositely charged particles. Okay, in this case, the protons and the electrons. All right, so we're looking inside the atom. There is Coulombic attraction between protons and electrons inside the atom. Okay, there are 2 things that affect Coulombic attraction: the distance between the particles and the number of protons in the nucleus. All right, in other words, distance and charge. Okay, distance and positive charge. How much positive charge is affecting the atom itself, okay? How much charge is in the atom, I should say, okay? So these are 2 things we're going to be thinking about while we try to justify the trends. And that's the big thing and kind of tough thing about the trend, is we can maybe memorize what's happening, but we got to be able to explain why it's happening. It's the why that's the more important part, okay? One other thing to point out, and this is kind of a tough thing to realize, the attractive force is not divided among the electrons, all right? What happens here? We would normally think, let's say I have an atom with 4 protons and 4 electrons. Okay, look at this great drawing I have here. So 4 electrons in energy levels and 4 protons. I think a lot of people would think like each proton attracts 1 electron. Okay? There's 4 protons, 4 electrons. Each one will pull a different one on its own. That is not true. What's actually happening is all 4 protons attract each electron equally. The protons attract each one equally in terms of their charge. Now, the ones that are closer will be attracted more because we said distance matters, but those 4 protons attract all electrons the same amount due to their charge, okay? And that's what we're trying to say. This means that each electron is being pulled by the whole nucleus equally. So try to remember that as we go through these. So the first trend on the periodic table is atomic radius. And what atomic radius is, as it sounds, just how big is the atom? How large is the atom, okay? So using the little diagram here, if I go down the column, okay, the atomic radius is going to get bigger and bigger. And the reason for that really is you're adding more energy levels, okay? As you go down the column, you're going from 1s2 to 2s2 to 3s2 all the way down to 7s2. The principal energy level is getting larger, which means those electrons are getting added farther and farther away. And it turns out distance plays a larger role than charge. So even though the charge is getting higher, there's more protons, the distance is getting so much larger that, oh, sorry, I'm getting backwards there. Sorry about that. Yeah, no, I'm right. That the atom is not going to be able to pull those electrons in as well, and the atom's going to be a larger atom overall. So sorry about that. More distance will result in less pull, which means the atom can be larger. And again, the size of the atom, what we're looking at, is basically the size from the protons, the nucleus, to the very last electron. That's the size of the atom. That's the atomic radius that we're looking at. Okay? All right. What about the trend going across? Okay? Now, the thing is, I know it's confusing. I chose a picture where I'm showing it going from right to left. A lot of times, though, we do the trend from left to right. So we just got to change the word here. Okay? As I go from left to right, the atomic radius will decrease. Now, why will it decrease? Well, as I go across, again, think of electron configuration. I go 2s2, I go 2p1, 2p2, 2p3. Each new electron is being added to the same energy level. So the electrons are not getting any farther away, but what am I increasing? I'm increasing the atomic number. I'm increasing the protons. And so as I increase the number of protons while keeping the distance basically the same, those protons are actually able to pull that atom in a little bit more, pull those electrons in a little bit more. So what we would see is that basically as we get closer, I'm going to use like oxygen as an example. All right, if I use oxygen with its 8 protons, I should have used an easier example. 1, 2, 3, 4, 6, 7, 8. Okay, 1, 2, and then 1, 2, 3, 4, 5, 6. What happens is all of these protons are pulling on each of the electrons. And what happens is that pulls all the electrons in a little bit closer. So now the radius of the atom, it's almost like the energy level shrinks. Okay, the whole energy level goes in, and that makes the entire atom smaller. So it's because we're adding to the same energy level, but we're adding more protons, which is going to pull all of them more in. Okay. Now, when I talk about these trends, this generally does not include the noble gases, because when you have the noble gases and when you form the perfect octet, they actually become a little bit larger, because when you have all those electrons perfectly set up, there is a repulsion that basically develops between them, and they become stable by just expanding just a little bit more. Okay, it's a little bit weird. That's kind of the best I can explain it for now, okay, or that we need to know. All right. So I am looking from the trends basically from group 1 to 17. Okay. As for ionic radius, this one's just kind of strange. Okay. I don't want to get into this one too much. I mainly want you to see a few things. First off, a cation is going to be smaller than the neutral atom. Okay. And it's because there's going to be more pull of the nucleus on less electrons. Okay. So again, because I know I said they don't divide it out, but it's the idea that, hey, you basically, one, generally remove that outer energy level, and so everything is now in even closer, and that's going to pull them all in. Okay, so it will be able to pull them all in a little bit more than if you left it at neutral. Okay, anions are generally larger because, again, you're adding more electrons while you do still have all this charge there. They're getting into a stable pattern, and therefore they do go out a little bit more. So anions are generally larger than their neutral atom. Okay. The trend we generally see is as you go downward, we again see that the ions will get larger because there's more energy levels. As you go across, the greater the positive charge means the smaller the ion. Again, you can kind of see that here. Okay, the more charge you have, the smaller it gets. Again, there are some variations there. This is where the trend is a little bit rough for ionic radius. And again, we're talking about the size of the ion now, not just the neutral atom. All right, there you go. Li plus is going to be larger than Be2 plus because you're, one, removing the whole outer energy level, and then you got all these protons pulling on fewer electrons. Okay. Greater negative charge means a larger ion. Again, that's because if you have more electrons, the protons are trying to spread themselves out more. They still pull on each one equally, but with each one, which they're more there, it makes it a little bit more difficult to continue to hold on to all of them. Okay. Ionization energy. This one's go back to kind of something that's a little bit more simple to understand. Okay. For ionization energy, what this means is it's the energy needed to remove the first outermost electron. That's what we're saying. So ionization energy is we want to be, how much energy do I need to pull that one electron off the outer edge? Okay. What we generally see here is as you move down a column, because the atom is larger, the outermost electron will be farther. Therefore, it's easier to pull off. So you have a lower ionization energy. Again, on my diagram here, I have the opposite. But if you go down, this would be decreasing. Okay, decreases. All right. So as you go down a column, because it's a larger atom, something else can come along and snag that one from farther away. All right. It's just the idea of, you know, if a wolf's trying to go after a herd of sheep, it's going to pull the one on the outside most likely versus trying to really get inside all of them and try to grab one. Okay? From going left to right, as you move left to right, the atom's getting smaller. Again, due to Coulombic attraction. The outermost electron is closer with greater nuclear attraction, so it's more difficult to remove. The ionization will get larger. Okay? So this is opposite of the atomic radius, that the ionization energy will decrease as you go down and increase as you go across. And it's because, as it just shows here, it works opposite of what the atomic radius is doing. Larger radius, easier to pull; smaller radius, more difficult to pull. Okay? The electronegativity. Okay? For electronegativity, the ability to pull another electron off. Basically the same reasons as ionization energy. The smaller the atom, the closer the nucleus is to attracting the electrons on the outside, the higher electronegativity. In other words, the atom's so small that the nucleus is able to reach outside the atom and grab other electrons, is what I'm trying to say. The larger the atom, the farther the nucleus is to attract electrons outside the atom, so there's a lower electronegativity. So electronegativity increases as you go across, and it decreases as you go down. All right? So, some of the things you might be having to do with this is, besides being able to justify why it will occur, you might have to be ranking elements based on electronegativity, atomic radius, and ionization energy. Maybe ions as well. In general, when I give these problems, all the elements are on the same row or they're in the same column. When I start shifting things all over the place, that gets it more difficult to really see. So I leave it within a row or a column because you should know the trends along those groups. Okay? So one of the things to see here is, you're showing all of the different trends. Is, again, ionization energy. Electron affinity is the same thing as electronegativity. Okay? So ionization and electronegativity work together. Atomic radius works opposite of those two. Okay? This is, again, showing where everything is increasing. Which way is it going? One thing I also like about this is the two middle arrows. They're showing you metallic character moves basically from the top right down to the bottom left corner, and non-metallic character works opposite. Again, it's basically saying which types of characteristics are you moving toward on the periodic table. All right. Now, I'll tell you, remembering trends was one of the biggest things I struggled with. Okay. So my suggestion that really helped me out eventually, okay, after taking even honors chem, I didn't really even develop this so much until AP chem and even college, is think about francium and fluorine, okay? Francium and fluorine, all right? Fluorine will have the highest ionization energy of any element. It is on the far right, all right, of the periodic table, and remember the trend increases all the way as you go to the far right. It'll have the highest electronegativity. Same thing. Again, a lot of times we ignore the noble gases on these, all right? But it'll be the smallest atom. So if you remember that, if you remember fluorine has the highest ionization energy, the highest electronegativity, and it's the smallest atom, if you move away from this atom, this element, the ionization energy and electronegativity will go down, and the atom will be larger than fluorine, okay? So that's the biggest thing. When you move away from fluorine, you can then see the trend. Okay? So ionization energy, if you move down from fluorine, ionization energy decreases because it has the most. When you move left, ionization energy decreases. You can also do the same thing with francium if you want to use that one, but it's obviously the complete opposite. It has the lowest ionization energy, the lowest electronegativity, and is the largest atom. So you just kind of have to flip your mind on that. Okay? And that is it. Very, very, very good job. Have a good one.